Well, hello and welcome to a module on the Otto cycle, analyzing the Otto cycle. And the Otto cycle is a thermodynamic model basically for your car's engine. And so this is like modeling the real world in your thermodynamics class. So let's go ahead and get started. It's my hope that you kind of recognize what this is all about. So this is basically an automotive engine. Okay? And here's what we're going to cover in this module. I'd like to take a little time to compare the diesel engine with the Otto cycle engine. I'll give you a little crash course on that. And then we're going to get into two specific problems to solve, step by step by step. We'll analyze the Otto cycle using the ideal gas model with variable specific heat. And then we're going to do that exact same problem, but we're going to hold specific heat constant. And then we'll numerically compare the two ideal gas modeling approaches. So here's the crash course where we'll compare the diesel cycle to the Otto cycle. Well, here's a couple of screenshots of engines, automotive engines. One is a diesel engine that you see in some cars, and lots of trucks, lots of the larger trucks, of course, are diesel engine powered. Okay. And then here's basically a gasoline engine, and we're going to model that with the Otto cycle. So look, they look very similar, don't they? And in fact, you're probably going to see some, well, wow, looks like the classic piston and cylinder here in cutaway view. So now you're thinking ahead, oh yeah, I've already done some things like pistons and cylinders, so I'll have some level of comfort getting started here. So let's look, how is the diesel engine and the gasoline engine, how are they similar? Well, we're going to model them both as a closed system, a fixed mass contained within a piston and cylinder. Both of those engines are going to be thermodynamic models. So we're going to model them with two basically modeling techniques for thermal systems, okay? And the other thing that they do have in common, both diesel and gasoline engines, is what's the heat source? What's the heat source for those engines? The heat source, as you well know, is combining fuel, a hydrocarbon fuel, with our surroundings air. And we do that within the piston and cylinder. And that's how we get our heat source that we're going to model the combustion process as a heat addition process. Now, both of those engines are going to be well modeled with our high-level schematic, a black box schematic operating in a cycle. That cycle is giving you, each time it completes a cycle, it's giving you some net work. It's taking heat from a high-temperature reservoir. That would be our model for the combustion. And then it's rejecting heat to a low-temperature reservoir. And that's going to be what we're going to do is thermodynamically model the exhaust process of your automotive engine. Also, how are these two engines similar? They're similar in terms of thermal efficiency, the energy sought over the energy that cost. In other words, W net, what we're seeking to produce, divided by what costs us out of our pocket, the heat source, QH. And then finally, what these have in common is the mean effective pressure. And I'm going to have to admit that I have to go back to the textbook as well and remind myself, what's the definition of mean effective pressure? This is not something I have memorized. The MEP, the mean effective pressure, is defined as the net work in kilojoules for one cycle divided by the displacement volume in cubic meters. That's the change in volume of the piston and cylinder as it goes through one cycle. That's the mean effective pressure. Now let's talk a little bit about how these two engines are different. Let's compare the diesel engine with the Otto cycle engine. fuels. Well, they are different fuels, aren't they? And at least in my world, I can tell the difference in the two fuels from the smell, the odor. So there's a distinctive odor of diesel fuel and there's a distinctive odor of gasoline fuel. Of course, they're chemically different, but both are hydrocarbon fuels. Okay. Spark plugs. Now, this is something that my dad taught me, but I'm finding that some students didn't know that for a car engine, automotive engine, we call that the spark ignition type engine. A spark ignition has a spark plug in each piston. Each piston and cylinder has a spark plug. So spark plug, yes, for the spark ignition engine, no spark plug for the diesel engine. Well, how do we initiate the combustion in a diesel engine without a spark plug? It turns out that a diesel engine can operate at a much higher pressure. And so therefore, in the compression process, the combination of pressure and temperature is what ignites the fuel and air. So there's no spark plug in a diesel engine. The reason I bring that up is the way we thermodynamically model the combustion speed, the speed of combustion. On the Otto cycle, also the spark ignition cycle, we're going to try to model that as instantaneous combustion. In other words, the spark sparks and instantly lights off the fuel and air, and you get an instant release of energy from that combustion process. Now, we're going to model the diesel combustion process a little slower than that. And the reason is that combustion wavefront is going to propagate a little slower because there's no spark there for that immediacy of combustion. Okay. And the way we're going to do that with our thermodynamic model is we're going to model the combustion heat addition process as a constant volume process for the Otto cycle model and a constant pressure process for the diesel cycle model. Let's hope my voice settles back down. Go to the next slide. Keep our fingers crossed. Okay, let's start with a sketch, like I always talk about. Here's the equipment sketch. So with your eyes, you see a piston and cylinder. It's fitted with a spark plug. Okay, little dashed line, that would be the air contained within the piston and cylinder. That's our system. That's our ideal gas system. For those of you that are familiar with automotive engineering, little jargon, top dead center. That's when the piston reaches its maximum travel. That would be the minimum volume contained of air inside our system. Bottom dead center, that's where the piston is fully, as far possible, removed from the top of the cylinder. Bottom dead center, that's where the volume is a maximum. Okay, so with that sketch, now let's move over to our pressure volume diagram. And let's quickly look at the process. We're going to start at state 1, which is the lowest pressure and lowest temperature in the cycle. That would be like ambient conditions, kind of like atmospheric pressure, atmospheric temperature. Okay, that's at bottom dead center, maximum volume, V1. Then we begin the compression process to compress the air in the piston and cylinder. And we're going to do that reversibly and adiabatically, 1 to 2. Let's see, can you visualize the work? I can. The work, integral PDV for a closed system. It's going to be negative, integrating right to left. Reversible adiabatic, QN for 1 to 2, that's 0. Okay. Next process, 2 to 3. This is our thermodynamic model for the heat addition process. QH, that's Q from 2 to 3. That's going to be a big number. It's going to be a positive number. How about the work from 2 to 3? Can you visualize the work from 2 to 3 from your previous work in thermo? Sure you can. The integral of PDV from 2 to 3, that's 0. There's no area under the curve. All right. Process 3 to 4. Reversible adiabatic expansion. This is the power stroke. This is where you're getting the power. That's the power that's driving your car on the road. The power stroke. expansion process. It's going to be reversible and adiabatic. Adiabatic, zero heat transfer. The work from 3 to 4. Can you visualize it? Sure. Integral PDV, area under the curve. It's going to be a positive number. And then finally, our thermodynamic model for the exhaust process, our model is cooling the air back from 4 to 1. And so our thermodynamic model involves just air that's trapped within the piston and cylinder. So your textbook does a nice job of explaining the thermodynamic model compared to the physical model, where we have air, intake air, we add the fuel, we have combustion, power stroke, and then we exhaust the exhaust products to the environment. So anyway, this is our thermodynamic model for that real world process. And it's pretty darn good. Pretty darn good model. All right, now, compression ratio, jargon for folks that are familiar already with terminology associated with automotive engineering. The compression ratio is a ratio of volumes. It's a ratio of the maximum volume divided by the minimum volume. So it's a geometric expression, okay? It's not a pressure ratio, it's a compression ratio. It's a volume ratio. And in the textbook, that's little r. Little r is the compression ratio. We're getting near the end of the crash course and we're going to get into problem solving, but I want to point out something for your homework solutions. When you read a homework assignment and you see the word air standard, that's some jargon to you. And so here's what it means in my first yellow text box. Second text box. When you just see air standard, what that means to you is you've got air treated as an ideal gas with variable specific heat. Now, what does that mean? That means use table A22 to get your properties, U and other properties, internal energy, that type of thing. Some of your homework problems, you're going to see the jargon cold air standard. That means something slightly different. And I've taken a screenshot out of your book under section 9.1, would like you to read the book. So here's what cold air standard means. It means something slightly different. It means treat the air as an ideal gas, but treat the specific heat as a constant value, a constant number. So that means go to table A20 and select a single value for C sub V and K. Remember, K is C sub P over C sub V. And select that at around T1, around ambient conditions. So that's just an important little jargon for your homework problem solutions. When it doesn't say cold air standard, that means air standard, that means variable specific heat, and that means use table A22. That's the end of the crash course. And now let's work through a problem start to finish, step by step. Now, and so I'll read the problem. Hopefully you'll read along with me. An air standard Otto cycle engine, Otto cycle spark ignition model, it operates with a mass of 0.65 kilograms contained in the piston and cylinder there. At the beginning of the compression process, state 1, the pressure is 100 kPa and the temperature is 290. That's about ambient conditions. The compression ratio is 8. The maximum temperature in the cycle is 2200 degrees K. Now, model the air as an ideal gas with variable specific heat and determining the following things. The displacement volume. Okay, that's the volume from min to max. The heat added. The thermal efficiency of the cycle. And finally, the mean effective pressure. So 4 things that we need to find. We'll go through the analysis and we'll be done with the problem. All right. Start with a sketch. So I'm going to repeat the sketch of the Otto cycle. So we're starting at point 1. Let's plan our work a little bit. What kind of things will we use to analyze this cycle that involves air? we're going to use the ideal gas equation of state, PV equals MRT, ideal gas equation of state. We're going to use that over and over. We're going to use the first law for a closed system over and over. Qn minus W out equals delta U. And remember, delta capital U is M times the change in little u, U final minus U initial. And so we're going to use that first law over and over and over again. We're going to use it 4 times. Okay, so let's see. And then what do we need to do? To find thermal efficiency, we need the net work. So if we tabulate our work, we simply add up all these works. There's only going to be 2 non-zero works. We'll add those up to get the net work. And all we have to do is worry in QH, where the heat is added, is 2 to 3. And that's going to be the denominator for thermal efficiency, W net over QH. We've got that. And then finally, we're going to plug and chug for mean effective pressure. Okay, so that's our plan. That's our plan. Many students get confused. This is a complex problem, okay? Many students say, I don't know where to start. And the professors say, well, you just look at the given data and you'll figure out where to start. And that is true. You're going to scratch your head, look at all the given data, and you will discover that what's given. Well, let's see. In the problem statement, we were given M, R for air. I know what that is. That's easy. And you were also given T1 and P1. So you scratch your head and you say, where do I start? Well, at least I might as well just calculate V1, because that's would be a good place to start. I'll calculate V1. Okay, great. We'll use the ideal gas equation of state. R for air, you determine as 0.287. If you don't have that in your head, 0.287 kilojoules per kilogram degree K. Remember that T has to be an absolute temperature, okay? And you'll calculate that V1 is 0.54 cubic meters, 0.54 cubic meters, okay? At least we've started. Now, what logically will be next? Well, we've got to do a cycle analysis, so logically it makes sense to start going, analyze 1 to 2, and then 2 to 3, and then 3 to 4. That's what makes sense to do. Okay, so in doing that, I think the next logical step would be to determine the displacement volume, especially since the compression ratio was given. The compression ratio that was given was 8, and that's simply V1 over V2. So V2, that's the minimum volume, the volume at top dead center. We didn't have that, but we just got finished calculating V1, the volume at bottom dead center, okay? So again, now it's pretty easy, plug and chug. So V1 is 1/8, I'm sorry, V2 is 1/8 of V1, okay? So V2 is 0.067624, there's V2. The displacement volume is simply the difference between the two volumes, max minus min. So the displacement volume is 0.4734. So if you're doing a quiz, at least you have like a 3 on the quiz. There's the displacement volume. Okay, now process 1 to 2. Process 1 to 2, reversible and adiabatic. We have an ideal gas, closed system, okay? So and not constant specific heat. We're going to have to use table A22 to evaluate our properties, okay? And so I want to remind you about using V sub R and or P sub R in table A22. And so remember here, notice this column heading, you see P sub R and V sub R, okay? The column heading is delta S equals 0. That 1 there is a footnote, a little explanation for that, and it says for a reversible adiabatic process. Delta S equals 0, so you can only use V sub R and P sub R for an adiabatic process, and that's what we have for process 1 to 2. Reversible adiabatic, that's isentropic. Isentropic, delta little s is 0. Okay, so for an isentropic process, we know that the ratio of specific volumes from 1 to 2 exactly equals the ratio of V sub R values from 1 to 2, okay? And V sub R is called the relative specific volume. And you don't even have to worry about the units there because you're always doing with a ratio, always using a ratio. So, okay, so anyway, that is going to be a key refresher that you've been exposed to before. So be very aware of these columns in table A22. P sub R and V sub R only apply to reversible adiabatic or isentropic processes. Okay, so let's look up our properties at state 1. So we're gonna look up V sub R, and looking ahead, we're gonna need the internal energy U to do our first law analysis on process 1 to 2. So let's write two numbers down out of table A22 for state 1. So we're going to write down V sub R, VR1, 676.1, and U1, 206.91. We're just going to write those two numbers down. Now we're going to do our analysis because we've got to find U2. We have to find U2, and we also have to find T2. Okay. So the way we're going to do that is recognize that 1 to 2 is isentropic. Okay. We looked up VR1, so we're going to solve for VR2. So VR2 equals VR1 times V2 over V1. And we have both of these. V2 over V1 is 1/8, isn't it? Okay. So VR2 is 1/8 of VR1. VR2 is 84.51. Oh, yay. Now, what do we do with 84.51? We go back to table A22, and we have to eyeball the VR columns and carefully see. I'm looking for 84.51, and I start looking for the trends. Oh, I see over here. Okay, I'm in between two numbers. Okay, 84 so I'm going to have to interpolate, and I'm going to have to interpolate for U and for T. So in other words, U2 is going to be somewhere between 473 and 481, and T2 is going to be somewhere between 650 and 660. And so I've got to do the interpolation. And so I just got to write on your paper, or in my case, Excel. I've got to set up a little table and do the linear interpolation to find U2, 475.11, and T2, 652.40. Does that make sense? Yeah. These numbers are in between these numbers. Okay, feel pretty good about that. So we've got U2 and we have T2. Okay, so at least we've got something. Okay, well, what's our next step? Next step is we're going to need the work done. It's going to be a negative number. The work done from 1 to 2. Let's write the first law. First law from 1 to 2. Q in minus W out equals delta U. Q, that's 0. So the work from 1 to 2 is simply U1 minus U2. I just found those two numbers. Look, wow. So little W out that I'm showing up here is negative 268.2 kilojoules per kilogram. My mass, 0.65 kilograms. So the work out in kilojoules is negative 174.3. We're getting somewhere. We're getting somewhere. We found the work out, negative number, compression work, okay? Negative 174.3 kilojoules, 1 to 2. Okay, we also found T2. So we can use the ideal gas equation of state to find P2. Now, in my Excel method, what I did was I remembered the jingle. P1 V1 over T1 equals P2 V2 over T2. So I wrote down the jingle and I studied on what do I have. Well, wow, I've got V2 and T2, and I've also got P1, V1, and T1. I've got 5 things out of 6, so I can solve for P2 is 1799.72. Okay, so here's the pressure P2. Now you say, wow, I couldn't remember that jingle, but I did remember the ideal gas equation of state. It is perfectly valid to solve for P2 this way. You know the mass, you know R, you know T2 and V2, so you can solve for P2 with an identical approach. Okay. Alternative way to find P2. Okay, so now we've got P2. We're marching through the cycle analysis. Okay. All right, so now what we're going to do, looking ahead, we've got to analyze process 2 to 3 for heat transfer. The work you can see, I'm getting ahead of myself. The work is 0 from 2 to 3, right? But we need to find P3. We've got to find P3, okay? So observe with your PV diagram, you couldn't do this without drawing a PV diagram. V3 equals V2, okay? And so we'll use again, the jingle or the ideal gas equation of state, either PV equals MRT or P3 V3 over T3 equals P2 V2 over T2. Either way, to solve for P3, that's 6069 kPa. 6069 kPa, it's P3. You say, okay, wow. Well, why did I need to do that in the first place? Okay, because I know T3, so I can look up U3, and okay, so process 2 to 3 is in good shape. Well, looking ahead, I'm going to need to analyze process 3 to 4, and so that's why I needed to find P3. Okay, that's why I did that. Okay, so looking ahead, we're going to use the first law for QH. In other words, Q from 2 to 3, the heat added. Okay, we need U3, and we know that T3 is given 2200 K. Also, we're going to need VR3 when we analyze process 3 to 4. So we're going to write down two numbers out of our table A22. We'll go to temperature 2200, and we'll write down U3 is 1872.4 kilojoules per kilogram, and VR is 2.012. VR is 2.012. We'll write those down. Okay. T3 was given in the problem statement. Okay. Now we're ready to use the first law to solve for the heat added. Okay. Let's see, the work is 0, so I strike that out. Q from 2 to 3 is U3 minus U2. We just got both of those numbers, and so U3, little U3, 1872.4, we just looked up, okay? The mass we have, and so Qn, the heat added, QH, 2 to 3, is 908.2, okay? Which is simply M times U3 minus U2. Work out was 0. Now we're going to move on to process 3 to 4. That's the power stroke. That's the expansion process. Okay. You see the repetition, same drill. So for the isentropic process, well, look, we know V3 over V4. That's going to be V1 over V2. Go back and look at the PV diagram. Okay. Let me go back and look. V3 over V4. Here's V3. Well, that's the same as V2. And V4, that's the same as V1. So that's how come I say we know V3 over V4. That's 1/8. V4 over V3 is 8, okay? We also know for the isentropic process then, V3 over V4 equals VR3 over VR4. We just looked up VR3 so we can solve for VR4, which is, okay, so we're going to do the math, okay? VR4 is 16.096. Back to table A22, and so I do my shopping. Oh, and I see here I'm in between two numbers, 16.946 and 16.064. So my T4 is somewhere between 1140 and 1160. Okay, my U4 is somewhere between 880.35 and 897.91. Set up my interpolation table again and solve for U4, which is 897.27. See, I did that linear interpolation. I'm hoping you're seeing the repetition. Okay, It's complex, but it's a lot of repetition. Okay, so first law for the closed system, process 3 to 4. Isentropic process, reversible adiabatic. So Q from 3 to 4, adiabatic. 0 minus W 3 to 4, what we're looking for, equals U4 minus U3. So therefore, the work from 3 to 4 is U3 minus U4. We just found U4, and so here's our mass. And so little W out is 975.13 kilojoules per kilogram. So capital W out, we multiply by the mass to get 633.83 kilojoules. Woo! Okay, we're getting close. So man, it was tough, but we're getting close. Hopefully we've got a little table of values in our homework. We can now calculate W net. Only two. We started negative 174 was the compression process, plus 633.83 kilojoules. Expansion process, or our net work, is 459.5 kilojoules. Okay. We're looking for thermal efficiency. We already had QH. We found that, Q from 2 to 3. So now it's a matter of going back in our problem and fishing out our numbers to get W net over QH is 0.506. Okay, now we're really moving along. We will go back and refresh our memories on the formula for mean effective pressure. This is one that I did not have in my memory banks, so I have to write it down. So the mean effective pressure is W net in kilojoules divided by the displacement volume in cubic meters. So in other words, it is 970.7 kPa. You say, whoa, where did I get that? If you work through the units, a kilojoule is a kilonewton meter, isn't it? A kilonewton meter divided by cubic meters. Okay, so that means kilonewtons per square meter, or kPa. So the units are correct. The mean effective pressure is 970.7 kPa. A lot of work. Okay. Whew. Almost have to pause to catch my breath. Okay. The second problem is identical to the first problem. However, except for the last part, so all the given information is exactly the same, except we want to model the ideal gas with constant specific heat. And for running through this example, let's say we're assigned cold air standard. In other words, we're going to select a specific heat and a value for K at T1, or at ambient conditions. Okay? I'm going to post the static slides for this out on my Jay's Toolbox website in case you want to go back and look at the details slide by slide if I've put you to sleep with the video. Okay. We're working on example 2. The first thing to do is select a value for C sub V and K. Remember, K is C sub P over C sub V. And what I did, just to save time, was, look, I realize that our temperature T1 is 290, and I see a temperature tabulated of 300. Rather than interpolating, it's common practice to simply select our C sub P value and K value at the tabulated 300 degrees K. So I'm going to write down K is 1.4 and CV is 0.718 right out of table A20, and then move ahead. Okay, we're going to hold those constant. What's our approach? It's exactly the same as what we did in problem 1. So I'm not going to repeat. So remember, we've got we're going to step through all of the processes. We've got 2 instances of work non-zero, 1 to 2, negative, 3 to 4, positive. And we only have to worry about process 2 to 3 for heat added. That's what's going to give us our thermal efficiency. We're going to start exactly the same place, and we're going to get exactly the same result for the initial volume, because PV equals MRT, and it doesn't depend on specific heat, does it? So we've got exactly the same result for V1. PV equals MRT at state 1. the displacement volume. Exactly the same result, because the compression ratio is 8, and we saw for V2, displacement volume is still V1 minus V2, exactly the same result. Now okay. A little note about analyzing isentropic processes, reversible adiabatic, for ideal gases with constant specific heat. And so I'm going to chase you back to your textbook, back to your class notes, back to your professor, who you've got this familiar thing, I hope, in your head for those situations, for an ideal gas that has constant specific heat undergoing an isentropic reversible adiabatic process. The result is PV to the K equals constant. PV to the K equals constant. We're going to exploit that for our two isentropic processes. Isentropic process 1 to 2, we're going to mimic what we did in the first example, find P2. We've got to go step through our process. We're interested in finding what's P2. We're going to use PV to the K as constant. So we're going to say P1 V1 to the K exactly equals P2 V2 to the K. And let's look at our relationship. P1 we know, V1 we know, K 1.4, P2 we don't know, V2 we know now, K 1.4. And so look, P2 is equal to P1 times V1 over V2 quantity to the K. It is plug and chug. It is calculator work to get P2 is 1837.9 kPa. Look how easy that was compared to using table A22. We just found P2. Let's use the ideal gas equation of state. Either PV equals MRT for state 2, or P1 V1 over T1 equals P2 V2 or T2. Either of those defined T2, 666.25. 666.25. In this problem, I used PV equals MRT. Apply closed system first law for process 1 to 2. Find the work done. Okay. Darn it, I didn't include my PV diagram for visibility, but let's see. 1 to 2 was reversible adiabatic compression. 1 to 2, isentropic, adiabatic, and reversible. Q from 1 to 2 is 0. So again, same approach. W from 1 to 2 is equal to U1 minus U2. But this time, I'm not looking up my U values in table A22. I remember for any ideal gas, delta U is the integral of CV dt. Got to remember that, okay? CV is constant. I'll pull it out of the integral. So delta U is CV times delta T, or for case for 1 to 2, delta U is CV times T2 minus T1. So now we're back to plug and chug. And so the work out, if delta U, U2 minus U1 is CV delta T, we're going to apply that here in our relationship to get little w out is negative 270.14 kilojoules per kilogram. Applying the mass, capital W out is negative 175.59 kilojoules. A little easier to do than our table work. Same recognition as we're looking at process 2 to 3. The volume is constant, okay? So we need to find P3. We'll use that ideal gas law, okay? Especially with constant volume. And so we saw P3 V3 over T3 equals P2 V2 over T2. Let's see, the volumes cancel. So P3 is simply P2 times T3 over T2, or P3 is 6069 kPa. No work done for the process. We'll just write down the workout from 2 to 3 is 0. It's a good thing to write down if this is a quiz. Good thing to write down. It's worth partial credit. Now we can easily calculate the heat added from 2 to 3. The heat added. We'll apply the first law. 2 to 3, no work done. Now we're visually seeing no work done. Area under the curve, 2 to 3, 0. Q from 2 to 3 is U3 minus U2. Well, we just went through that dissertation. How do we calculate U3 minus U2 for an ideal gas with constant specific heat? It's just CV times T3 times T2 minus T2. So again, plug and chug to get little, oh darn it, I didn't solve for little qn. I just went ahead and applied my mass to get capital Qn from 2 to 3, 715.8 kilojoules. See how this is a little easier than the table work. Okay. We're up to process 3 to 4. Okay. We found P3. We're working through the cycle points. We found P3, and that's going to make it easy for us to say P4 V4 to the K equals P3 V3 to the K. Look, we know V4, that's V1, and we know V3, that's V2. And so we can immediately solve for P4. So P4 is 330.21 kPa. That's what P4 is. That's how we got P4. You say, well, why are we solving for P4? If we've got P4 and we also have V4, do you see that that enables us to find T4? That's how we solve for T4. P4 found. Find T4 using the ideal gas law. Okay, great. So we have PV equals MRT. So we're going to solve. So T4 is 957.6 degrees K. Okay, why do we need T4? Well, because we need to find the internal energy change for process 3 to 4 to get the work out. Here we go. Work out for process 3 to 4. We'll apply the first law. Qn, 0, because it's adiabatic and reversible, isentropic. Okay. Minus the work from 3 to 4 is U4 minus U3. Okay. Very repetitive. Okay. There's our expression for the change in little u, CV times 3, T3 minus T4. That's negative delta U, work from 3 to 4. Okay. I didn't explain that very well. I'm going pretty fast now. So the work out from 3 to 4 is, so let me slow down. The work out from 3 to 4, little w from 3 to 4 is U3 minus U4. That's the first law, 892 kilojoules per kilogram. Apply the mass to get capital W out, 579.83 kilojoules. Okay. Now we're back to tried and true definition. We're visualizing the net work. The net work is the area within this cycle. Just like you covered a good number of weeks ago, 4 or 5 weeks ago, you covered this, okay? The net work, we add up all the works. In this case, there's only 2 to add up, 404.23. Now we can find the thermal efficiency, the net work divided by the heat added, 0.565, 404 divided by 715.8. That was the heat added, process 2 to 3. The mean effective pressure, I still can't remember it in my head. So the W net divided by the displacement volume, W net over the displacement volume. Again, plug and chug in our calculator, 853.9 kPa. Kilojoules divided by cubic meters. The units work out to kPa. You can just about do that in your head. If you can't do that in your head, write it out with pencil and paper. Okay, now it's time to compare our results because we solved the same problem twice with 2 different ideal gas specific heat models. Here's our comparison. The displacement volume, identical with the two methods. But look at this variability. So I calculated the difference between these two numbers by using the variable C. I said, I'm going to figure that these are quote unquote the right answers, and I'm going to compare this model with the right answer. So I use this as my baseline. And look at this, For heat added, I've got a 20% difference. Net work, a 12% difference, 12% lower. In thermal efficiency, I've got about 12% higher, okay? Mean effective pressure, about 12% lower. That is a large variability. That's not enough to, we can't just slough that off and say, oh, yeah, that's about the same. How do we explain that? The way that we explain that is that when we used our constant specific heat model, we picked a number for C sub V and K at the lowest temperature observed in the cycle. If you went back to table A19 and you eyeball values for K and you eyeball values for C sub V, and you remembered the temperatures involved in our problem went up to 2200 degrees K. There's a lot of variability. And so our picking a single lower value for C sub V is really what explains this variability. It's not numerical errors that explains it. It is in lower values for a constant specific heat model. Okay, so we've spent a lot of time. I have to apologize a little bit for that, but for completeness, I wanted to work through two different methods of solution for the same Otto cycle analysis. So what's our recap? Otto cycle involves piston and cylinder, closed system analysis. It involves an isentropic compression and an isentropic expansion process that involved your analysis. Okay. The constant volume heat addition for the Otto cycle is what models the spark ignition combustion process. And the other kind of neat thing to remember about the pressure volume diagram for the Otto cycle model is that only 2 of our 4 processes involved work. The other 2 did not involve work. There's the little that's a nice V8 engine. Okay, we've been through a lot, and I want to thank you for hanging in there and watching it. There may be some advantage to you downloading those static files and going through them at your leisure to see step by step how we analyze an Otto cycle using the 2 different models, air standard and cold air standard. I hope that helps.